Good afternoon, everybody, and welcome to our webinar. We would like to give thanks to everybody who has joined us today, and the Chatbot team would actually like to extend their warm welcomes and thanks also to Raiseti for joining us. I am the marketing coordinator for Chatbot, and today I will be your host. I want to take you guys through the agenda. We will start with an introduction, which will be played by a video. And then I'll hand over the platform to Raiseti, and we'll do a Q&A session, which would be live. So please, guys, pop your Q&As in the comment section, and we will be answering them at the end. So without any further ado, I'm going to now play the video, and I hope you guys enjoy. Awesome. So thanks once again for everybody joining and our guest speaker. We're so excited for this talk. If you guys have any questions for us at FinChatbot, please feel free to contact us at marketing@finchatbot.com. Or if you want to find out more about our company and what we are so passionate about doing, please visit our website. It's www.finchatbot.com. I'm going to now hand over to Raiseti. Floor is yours.
Hi, everyone. My name is Raiseti, and I am a computer vision researcher, currently working on work that has to do with satellite imagery and creating ground truth labels. And in today's talk, I'm going to be talking about some of the research that I've done in the past, and also a lot about like the broad view of how to create great data sets when you're working on when you're working with machine learning problems. So let me just share my slides. Awesome. So feel free to ask questions during the talk. You can pop them in, and then at the end of the talk, then I can just go through all the questions, and then we can have a discussion about anything really regarding this talk. So how else do we think about creating ground truth data sets to answer research questions? This is the topic that I'll be going through today. And the motivation really for this is that, I mean, as researchers, especially as computer scientists, we are very interested in solving impactful real world problems. It's fulfilling, right? However, especially like problems experienced in countries like South Africa or like other developing countries. But the problem is the lack of ground truth labels in these countries. And that sort of impedes us from being effective in sort of trying to solve these real world problems. So in this talk, I'll be going over some of the more some of the creative ways to create ground truth data sets in order to help us use machine learning to solve these problems. So to give you context on what we are talking about, the keyword for today is ground truth. So just to give you context on what that sort of means, this is the reality that you're actually trying to predict. So this is the data that allows you to be able to actually help the models that you are building be able to mimic the reality that you're actually trying to predict with these models. So what that sort of means in computer vision, this means if you have satellite images, for example, some ground truth would, the guidance or some ground truth labels would be maybe something that tells the model where maybe buildings are, for example, or if you have medical imaging, medical sort of images, the ground truth would be some sort of like labels that show your model where the areas of interest are. So where the pancreas could be, or the heart, or the kidneys, or things like that. So similarly, if you have like a cityscapes kind of setting, the ground truth labels would be where the people are, where the cars are, or where the roads are, and things like that. So as you can imagine, creating these data sets could be labor intensive. I mean, think about creating this data set, for example. So for a machine learning problem, you would need hundreds of thousands of images like this to be able to have a model that converges to something that makes sense. And what that sort of means is that you should have, so per image like this one, you would need to label each and every pixel in this image accordingly. And you'd have to do this for the 100,000 images that you might have. And this quickly becomes very labor intensive, expensive as well. And your, like the people who are actually labeling this data set for you will have to be like well coordinated. And the data set should be validated. I mean, imagine you work with maybe 15 or 20 or even 100 data labelers to label one specific data set. You would want the answers that they provide to be coherent with each other. Otherwise, you would have people labeling some pixels as something and then the others labeling the same pixels as something else. And that would not be effective for your machine learning models. So this usually requires rigorous evaluations and coordinating for you to be able to get these data sets well labeled. So in this talk, I'll be going over 2 case studies, one in which we try to use pre-existing algorithms to generate ground truth labels. So instead of having people to label all these images in the data, can we actually use pre-existing algorithms to label these instead, in order to sort of remove those costs that I've spoken about. And in the second case, can we use other existing ground truth labels to, can we put them together so that they can help us answer some new research question that we might be interested in and don't have the labels for. So looking at this frame here, this is a clip of one of the very busy intersections in Jakarta, Indonesia. And this is just the CCTV footage of this intersection showing traffic and some violations like this one that governments might be interested in. So for this project, we wanted to know if we can actually use pre-existing algorithms in order to collect data from scenes like that. So this was a project which was done in conjunction with the Data Science for Social Good Fellowship with the University of Chicago. And we worked with the city of Jakarta and Pulse Lab Jakarta to actually realize this. So what the partners were actually interested in, they wanted to improve traffic safety in Jakarta, Indonesia. And so the issue was that they didn't have ground truth labels to help them achieve that goal. So the question they were actually interested in was, can they extract data from these traffic footages in order to inform possible interventions? So can they collect evidence of, I don't know, like traffic jams at 3 o'clock at intersection X, so that they can then be able to support having a traffic officer at that intersection at that time, things like that. So they didn't have any ground truth labels to help them achieve that. However, they wanted to use existing algorithms in order to extract this kind of data. So for some context, the city of Jakarta in Indonesia has been growing at a very rapid rate. So between 2000 and 2020, the city has just steadily been growing. So people have been moving out of other parts of Indonesia into the big city, mainly for jobs and other things like that, like quality of life and things like that. But then the city itself had not sort of planned for this um, high rate of people moving into the city. So as such, they didn't have enough infrastructure to actually support this this growth. So as a result, uh, there are a lot of people. There are a lot of people with cars, private cars, and private motorcycles and things like that. And this is just a typical peak hour sort of traffic sort of vibe in the city. So just imagine it's like 9 a.m. or something, and everyone is just trying to get to work at the same time. So there are huge traffic jams in the city, and everyone is just trying to maneuver traffic so that they can just get to work. As such, that creates like a very high traffic safety issue because there is just no order. So the government wanted to know how much of this is happening, where it's happening, so that they can be able to employ different interventions to help ease these problems. So some of the problems they wanted to know about were like in which intersections are vehicles driving the wrong way, for example. Where are people illegally parking? Where are people stopping where it's forbidden, causing traffic jams, more traffic jams? And where are the street vendors sort of located so that, because they usually force pedestrians to, they usually occupy sidewalks, so they force pedestrians to actually use the road instead of the sidewalk because they're occupying them. So that creates traffic safety problems. So some of the interventions they were interested in were of these intersections they had, where should they put like more traffic lights? Where should they put traffic officers, and at what time would be efficient, most effective? And for some places, where can they actually put more money in to improve the infrastructure? And others, like how can they effectively um, uh, get more public transport routes in the city? So what they had was, so they didn't have any ground truth data. However, what they had were over 5,000 CCTV cameras, which were spread across the city. And these cameras were not all owned by the government, but privately owned mostly. However, the government had access to them. So at that moment, what they had was like some people who were watching these cameras, these video footages and collecting data. So someone would just sit and watch like an intersection and collect data on that intersection. However, scaling this to the however many intersections they would have and be interested in would require more people doing the same thing and doing that. So that would mean this is very highly unscalable, and the government wanted like a more efficient way to collect this data so that they can be able to get information about their intersections. So our solution was to use a machine learning model to help extract this data that they're interested in. So instead of having multiple people actually watching these cameras, we would have multiple computers actually extracting these points of interest in these data sets. So to do that, given a traffic footage like this one, what we did was to use an object detection model to identify the objects on the road and where they are. And we used an optical flow model to actually label the objects which we had detected as moving or not, and if they're moving, in which direction are they moving. And then we used semantic segmentation to find out where these objects which we have identified are moving at. So are motorcycles moving on the sidewalk, or are they moving on the road, or are cars stationary on the road, or are they stationary on the sidewalk, and things like that. And what time of the day are they doing that? So those are the things that's the solution that we actually provided. And just to go into more details about how these models actually work, I'll start with the object detection model. So this was work which was done in 2018. And so this was work which was done in 2018. And at the time, the best model was the YOLO V3 network. And how YOLO works is, so because we had videos, right? And a video is just a collection of image frames. So the model looks at an individual image frame as input, right? And then it scales it accordingly. And then throughout each scale, it creates like these grids of different sizes. So for a very small scale, it would create like bigger grids and then perform object detection on each and every grid. So similarly, on the other scales as well. And at the end, it would consolidate all this information to say, okay, so maybe at these pixels, at grade 1 and 2, for example, it was background, but then we found like something like a dog, but then the next the next two grids would say, yes, it was a dog with maybe 90% accuracy. And then the next scale would also say this was a dog. And then that way it would refine the bound of that, like the extent of where that dog is actually occupying the pixels on the image. So this was very good for us, given that we had objects like motorbikes with people usually on them. So if we were able to get a model that would look at not just the entire image, but then different parts of it, it was good for us to be able to actually locate exactly the extent of the motorcycle into the bounding box. So this model worked really well. However, it was only pre-trained on the COCO dataset. And what this meant for us was that the COCO dataset did not include objects which you usually find in Jakarta, such as minibus taxis or tuk-tuks and food carts. So the model didn't know what to classify them as when it actually found those objects. So usually it would classify a minibus taxi as a bus, or a tuk-tuk as a bicycle. So for us to be able to understand what those objects are, we had to label another set, like a subset of the data that we had, and fine-tune the model so that at the end, the model is able to understand what those objects are. So that's how we did the object detection part. And to do the motion detection part, we used an optical flow model called the Lucas-Canard method. And how this method actually works is that it looks at a neighborhood of pixels. So instead of one pixel at a time, it looks at a group of pixels and then follows that group through the frames. So if that group of pixels has moved or changed position from the first frame, then it would classify that group as in motion. So imagine, so you're tracking multiple groups of these pixels, and at the end, you are able to actually capture the parts of the video frame that are moving. And because we know from our object detection model, where the objects are, like the bounding box of each object, we're able to see, to just get an intersection of the pixels that are moving and if they're in the bounding box or not. So if they're in the bounding box, then that object which we have identified, then we can actually label it as moving or not moving. And another byproduct of the optical flow model is that we can also get the direction in which the object is moving. So we are able to actually find the car that is moving to the left or right relative to some direction that we might be looking into. So this model usually breaks when the objects in the frames move really fast. But then for us, this was not a problem because Jakarta had um, a traffic jam problem. So naturally, the cars don't actually move that fast because there's usually always a lot of cars or vehicles on the road. So in order to understand where those objects are moving, we use the semantic segmentation model, which is a computer vision-based machine learning model that labels each and every pixel in a frame. So given an image, the model would actually go on and make classification for each and every pixel in the frame so that at the end you have something defined like this. So you can actually see the extent of the road, and sometimes you would even see the barrier line or the dividing lines between the lanes of the road. You would see the extent of the sidewalk and where all the trees and everything in the sky is. So this is a very expensive model to compute. However, for the images that we were working with, the cameras were always stationary. So this is a CCTV camera on like a pole or in a tree or something like that. So it does not move. So which means these pixels will still be these pixels tomorrow until this camera moves. So we didn't have to do this frequently, although this was an expensive computational process. And in order to capture the entire road, we just had to wait until there were no cars on the road or there were less cars, and then we could capture the extent of the road and store that. So this is how we used pre-existing algorithms to actually help us extract data. So the data that we have extracted looks something like this. So from the data pipeline, we had as input the videos, but then for the object detection model, we were looking at each and every frame at a time. So we found out which objects are in the frame, and then the bounding box, so where they are in the frame, and then we start that information. We found for the stored information, for the objects that we found, are they moving or not? And if they are moving, then we're able to store that information as well and associate it with the objects. And then we are also able to identify where they're moving in the scene. So are they moving on the road or on the sidewalk? And then we store that information accordingly as well, so that at the end we are able to have results like a motorcycle which is moving on the sidewalk, and then be able to flag that that's information our partner was actually interested in, or cars that are stopped on the road, and then we're able to flag that. We also store information like the time of day these events are happening, and also where in the city these events are happening, so that the partner is able to just pull out for this intersection when are people actually, or when are these violations, at what time of day are these violations being made, and then they can actually intervene. However, like for example, traffic jams, which would be happening at 3 p.m. every day or 3 p.m. every Tuesday for some reason. So maybe a temporary traffic officer can be deployed at that spot. and then help traffic move smoothly. So that was the first part, but sometimes we have problems in which we can't actually use pre-existing algorithms like these in order to help us solve these research questions that we usually have. And for that, the question becomes, how can we adapt pre-existing algorithms, pre-existing ground truth data to help us answer specific questions? So for this second problem, we wanted to classify residential neighborhoods according to their types in South Africa. The problem was that, I mean, if we think about South Africa, there are some neighborhood types that are not so common across the world, or they don't look the same, like townships, for example. If we have data from Germany, for example, and we wanted to understand where the townships are, so generalize the data to South Africa and find where the townships are in South Africa, maybe that would be a problem because maybe the neighborhood looks differently in South Africa than in Germany, for example. So here we had other data sets in South Africa, but then they did not answer the question, like where are the residential neighborhoods, or what are the types of different residential neighborhoods we had. And for that, we wanted to use these other data sets, put them together and see if we can actually answer these questions. So this was work which was done as part of my master's degree at WITS. And the topic of the work was, can we use satellite images and computer vision to study the evolution of spatial apartheid in South Africa? So just to give you some context, the Spatial Apartheid Act was an act which was passed during the apartheid era that actually forced non-European groups out of like wealthy, mostly predominantly wealthy neighborhoods, such as suburbs and small holdings. And these people were actually displaced into places like townships. And this is an example of a township. This is a time lapse of Tembisa in Johannesburg over the years. So this is how it has grown. And the beige part is Tembisa. This part here is a small holding next to it called President Park. And this is just how they have evolved over the years. So Tembisa has grown over the years. And yes, it has consistently like grown, like the visual characteristics still look the same. So in a township, you would typically have densely populated buildings, like a dense population of buildings. And for each and every household, they usually have uniformly sized yards and houses, and in each, irrespective of the number of people living in the house. And in the neighborhood itself, the services like your hospitals and your schools usually serve a very large number of people compared to hospitals in suburbs or small holding neighborhoods. So this was during apartheid. And I mean, during apartheid, even the budget which was allocated to these township neighborhoods was disproportionate to those allocated to suburbs and more European sort of neighborhoods. So this was during apartheid, and after apartheid, we still see some of these characteristics of services which serve a huge population in townships, and in suburbs, we don't see much of that. So in this work, we tried to understand the extent at which this is happening. So just to also give you more context, these are images of South Africa. This is Cape Town in, I think, 2018 or 2016. So this just shows a township next to a suburb. Similarly, a suburb next to an informal settlement. And just visually looking at these two images, we think this is more of a computer vision problem. I mean, there is a clear distinction between a township and a suburb, an informal settlement, and a suburb, and as such, those kinds of comparisons. So for our work, we decided to use satellite images to label these neighborhoods accordingly. So can we actually demarcate the extent of townships or suburbs, different neighborhoods on satellite images? That was the question we were interested in. So the data sets we had available were satellite images of South Africa, the entire country. We had building data set of the entire country as well. So what each and every red point shows in this data set is a building. So this is a township. This is the same township, Tembisa, next to a wealthy neighborhood, President Park. And this is just the difference in density of buildings in a township versus in a suburb. And this is the enumeration area data set as provided during the census. And this just tells us that this part, this yellow part is of township, the blue part is of small holding, the pink part is an industrial zone, and so on. However, this data does not tell us the extent of these neighborhoods. So if it's saying this is a small holding, it just says everything here is a small holding. It does not tell us that this part of the small holding has not been built upon. So this is just land that is empty. Doesn't tell us that. So what we wanted to do was, can we understand the extent of buildings in a township so that we can be able to make further sort of analysis that involved requiring information like that. So for us to be able to get the extent of these buildings in this neighborhood, we looked at our building data set. It looked like this. So it just said here, it's a house. So it has a point to demarcate that. And what we did was, instead of having just a point, we inflated the point so that it covers the building. So the size of this point the size of this new polygon which we created, sorry, it's like a standard size that a standard South African house would be of. And then we did this for the entire country, irrespective of the size of the building itself. So after doing that, we got an intersection of where the buildings are with what the neighborhood type was labeled as during the census. So the yellow part is a village, the purple part is a farm, and the rest of the blue part should be vacant land. And now we are able to see that these buildings in red, in the red section here, are in a village. And then the ones in the green section are in a farm. And accordingly, these purple ones are in the part of land which is supposed to be vacant. So we're able to associate buildings with neighborhood types by doing this. And then because like these points, these are still individual polygons. So this could be like, I don't know, maybe this could be 700 polygons in here, and just working with data in this fashion is just not efficient computationally. So what we did was just to dissolve these individual buildings into like one big polygon that represented the neighborhood type. So the polygon in this greenish yellowish color would now represent all the buildings in a village, and the ones in pink, all the buildings in a farm, and then the other colors accordingly. So doing that for the entire country, but then zooming into just a part of Johannesburg, this is what the data set actually looks like. So you have like the light blue part being a suburb, the yellow part being the townships, the red parts being the informal settlements, and then the white parts being the background. So this is the non-built up area, and then the other colors accordingly. So this was divided into 12 classes, mainly because from the census we had 11 classes. The township, actually in South Africa, townships and suburbs are combined as into one class called formal residential neighborhoods. So in formal governmental text, you won't find townships anyway. They are all called formal residential neighborhoods. So what we had to do was to hand label where all these townships are, because although it's not written in these data sets, people in South Africa know where the townships are. So that's what we did. We collected that data set and then we labeled our data set accordingly. So comparing to other methods that we could have went with, we could have just used this data as provided by the census. So this would just tell us that this is a small holding or this is a wealth neighborhood, although this part has not been developed upon. So this data set would assume that there are buildings here, but we don't know where these buildings are exactly. And we're just saying the section is of a suburb. So we didn't want information data like that because it's a bit misleading when you're training machine learning models, too much noise. And there was this cadastral data set as well, which tells you about where the real estate ownership is in the country. And so these are as registered to the government, like the land plots as registered to the government. Again, people might have bought a plot of land here, but then not necessarily have developed it. The government wouldn't know that as yet. But then this is what the shortcoming of the data set is. So with our data set, we are able to find where the buildings are and then label them accordingly, according to their type. So reducing the amount of noise that could have come with the other data sets. So training a machine learning model, a semantic segmentation model to actually do this. So the data set we had was just for 2011 because this census data was done during the 2011 census and we don't have an update of this information. So for us to be able to know how the neighborhoods have grown or evolved over time, then we would need to find a way to track the changes and then label them accordingly. So to do that, we used a machine learning model. We trained the model on the 2011 data set, and then we made predictions for the other years. So how that model actually works is that because we are interested in the individual pixels more than labeling the entire image as of township, we use the semantic segmentation model, which takes in as input a satellite image and then labels each and every pixel, makes a prediction for each and every pixel accordingly. So this is a unit model, one of the models we had experimented on. And this is the kinds of predictions it actually gives. So given a satellite image of where small holding buildings are, this is the kind of prediction our model actually makes. So this is of a township. The yellow part is township and the white is the background. And we can see that our model is able to capture the background where it is. And then it makes confusion on some of the pixels, especially around the periphery, as those in a suburb. So this is what a suburb actually looks like. And I mean, usually they are characterized by trees and like buildings with roofs of different types. I like this, and they would be a little bit greener than a township. But you could see that maybe towards the end of the neighborhood, it looks a little bit green, and it could be why our model is actually predicting it incorrectly. So the results from this model, from training it on a 12 class algorithm, we have a 45% mean intersection of reunion, and the state of the art on a data set like ours on 10 classes has 54.96 mean IOU values. So what this actually, what the rest of the misclassifications sort of look like, they look like this. So given a suburb, this is a suburb, according to these labels. It looks like a village of some sort. I mean, they don't have trees, as suburbs could have trees and other characteristics like that. And they have big yards. These suburbs have big yards. So we could see somehow why this model could see it as a village. Similarly, a suburb could be misclassified as a township. I mean, some suburbs which don't have enough trees on the roads, like the other one that we have seen, could actually maybe look like townships after all. I mean, it's very difficult to actually capture like all these imagine suburbs in Cape Town versus suburbs in Johannesburg versus suburbs in, I don't know, Polokwane or something. They will actually look a little bit different. And having a model that has 12 classes of like, categories and one category of suburb, I mean, we are guaranteed to not be able to capture all of these variations accordingly. But then these are the labels that we wanted to create for this work, and further reducing the classes into more subtypes would definitely ensure more accuracy, but then we don't have that cost of labeling the individual suburb types, for example. So as an example, every neighborhood in these boundaries is actually of type suburb. So this is a suburb, this is another type of suburb, this is also another type of suburb, this is another type of suburb. And capturing all these variations in one class suburb could be difficult and expensive to label. So these are some of the shortcomings of our data set. So this work is actually, we're actually trying to, not trying, we are on the, like in the process of publishing this data set, and yeah, it'll be freely available for research use in a few months. So yeah, so looking at like what the overall data set actually looks like, this is a township in Soweto. This is Soweto. This is part of the township Soweto in 2011. So in 2013, this is the growth. In 2015 and in 2017, this is the growth. This is the same spot in Soweto. So with these kinds of models, we want them to be able to capture all this growth and label it accordingly. But then as you see from these 4 images, there are differences in texture. I mean, the quality of satellite imagery in 2011 versus that in 2017 and 15 is very different. So these are some of the other challenges that might come with building machine learning models like these, although you have ground truth labels. So the problem is usually not just the lack of ground truth labels. That is just one big problem. But then there are other problems of texture that you might have with like typical data sets like these that you create. So yeah, so this is, I think I should stop here, and yeah, I'll take questions from here. But then key takeaways from this work would be that every time you create ground truth data sets like these, thorough evaluation is always needed. Like you need to go over, see where the data set breaks, and then iterate, see if the labels that you've created, do they cover a lot of the cases, and what is a lot of the cases? that you are interested in. And this could be a very iterative process, and small mistakes usually are very expensive. And as such, you need to take proper care of how you actually create these labels. But yes, thank you.
No, thank you, Raisiti. It was such an interesting talk. I see that someone has put in a comment. I think it's Vianney who says this talk was amazing. So thank you for that comment. Got another comment. Thank you so much. This was a really interesting talk. And then another one that says thanks for that. Very informative. So I don't think we have any questions. I think we'll end it off here. So thanks again, everybody, for joining us. And we hope to see you again at our next webinar. We look forward to having you. Thanks again, Rossetti. Bye.